It is section 14.5, the chain rule and implicit differentiation. Here we have a recall chain rule for functions of a single variable. If y is f of x and x is g of t, a function of t, where f and g are differentiable, then y can be considered as a function of t. It is differentiable, and its derivative with respect to t can be obtained by using this formula, dy over dx times dx over dt. You learned this formula in Calculus 1. Now we'll apply this formula for functions of multiple variables. The chain rule case 1, suppose that g equals f of xy is a differential function where x is g of t and y is h of t. X and y are a function of t and they both differentiable. Then z is a differential function of t and its derivative with respect to t can be computed by using this formula. Now f is a function of xy, so that this is partial derivative with respect to x and dx over dt. X is a function of t, single variable, so we are using d notation. The same way here in y direction, y derivative, partial derivative, and dy over dt. Again, y is a function of a single variable t, so that we are using d notation. To understand this formula thoroughly, let's see this observation. Z is f of xy. Simply, we choose x times y. Now, x and y are functions of t, then we can write in this way, so that z can be considered as a function of t, and if we try to make derivative with respect to t, then by using the product rule, we have this formula. For this component, first we apply derivative, x prime and y, plus for this one, we apply derivative, so it's x, y prime. This is the product rule. Now let's see this formula. We make x derivative, then that'll be y, and dx over dt is x prime. And for that one, now y derivative, partial derivative, then x is the answer for that portion, and dy over dt is y prime. As you can see here, these two are the same. So you may consider this formula as a product rule. F is a function of xy, but x includes t and y includes t. So that for x, you have to make a derivative of f with respect to x and dx over dt. So x is a kind of a group or expression of t. So as in the chain rule, x, okay, here, x includes t and y includes t, so that for this one, you are making derivative, and for t involved here, you make another derivative. So that is a kind of a product rule. So that's the reason we get this formula. Okay. Let's try to solve this problem. Z is x squared y plus xy cubed. X is cosine t, y is sine t, And we want to find dz over dt at t equals 0. Okay. Now, dz over dt equal, now that's f of x, f sub x, x prime, plus f sub y, y prime, right? Okay, what is f sub x? X derivative, that is 2x and y from this one, and that is y cubed, and x prime, f sub y, then that is x squared, and this is 3x y squared, and here y prime. Now, once we try to get without evaluation, then you have to finish computation. Now, in this case, z is considered as a function of t, so that you have to replace x and y by using here cosine t and sine t. So that is, okay, let's try to replace x and y with cosine t and sine t. Then 2 cosine t and sine t, and plus sine cubed t, and x prime is now minus sine t, right? And then that is now cosine squared t, x squared, plus 3 cosine t, now sine squared t, times y prime is cosine t. So that is the final answer for this term. And now we try to evaluate the slope at t equals 0. Then by putting t equals 0, you can evaluate this value. Or you may use this one, and once t is 0, then we know that x is cosine t, cosine 0 is 1, and y is sine t, sine 0 is 0. X is 1, y equals 0, so that you may use that one, and you can finish it. So here, dz over dt when t equals 0, okay, we may use that one or that one, it doesn't matter. Okay, x is 1, y equals 0, then this will be 0, so no matter what it is, it doesn't matter. Now, so that's 0 plus, and x is 1, that is 0, so the 1, and y prime is cosine t, cosine 0, so it's cosine 0, which is 1, so that the answer, the final answer is 1. Okay, you can use this one or that one, but if you are asked to find dz over dt, then that one is the solution, final answer. Okay. We may solve a problem by using computer algebra. This is Maple script, and z is defined, and x and y is defined as a function of t, and we try to make derivative of z with respect to t, then that is output, and we can simplify, and this the value, and that means that the last output, this output is simplified to get that one, and we evaluate at t equals 0, and then the final answer is 1. Okay. Now here the main point is the chain rule is a kind of a product rule. So t appears, and in this example, t appears twice, so that like in usual product rule, we try to make derivative for the t in x, and now we try to get a derivative t in y. Okay? Okay. So along with that observation, we can generalize the chain rule quite easily. This is case 2. Z is a function of xy and differentiable, where now x is function of st and y is also a function of st, and both are differentiable. Then now we can get the derivative of z with respect to s and with respect to t. In this case, z can be considered as a function of s and t. And first, that's a function of x and y. Now, x and y are both function of s and t, so that z can be considered as a function of s and t, so multiple variables. So we use this partial derivative notation, round z over round s. Now, s is involved here, s is involved here. So that's the reason, first we make for that one, like in product rule, round z over round x, and round x over round s. Now, for y, round z over round y times round y over round s. For t derivative, similarly, we can explain it. Okay, let's try to solve this problem. Z is e to the x and sine y, x is st squared, and y is s squared t. Find these partial derivatives. Okay, let's try to find only this one. The other one is really almost the same. Okay, so we'll use that formula. So first we have to get z x derivative. Right? We have here zx, zy, g sub x. It's the same as e to the x and cosine y. And how about z sub y? Y derivative. Okay, there's e to the x and yeah. Oops. Now that one, I'm sorry for this one. Okay. Now we are working on x derivative. So for this one, e to the x, and this is a kind of constant, and z sub y, y derivative. Then we put this constant, and derivative of sine y is cosine y. Okay? Now we have to get x prime, x t derivative, and y t derivative. So x t derivative equal here 2st, and y t derivative, that is now s squared. So this product plus that product is the result. So z sub t is the same as this product, e to the x sine y, and times 2st plus, and this one, e to the x cosine y, and s squared. This is not complete yet. We are now considering z as a function of st. So here x and y must be replaced by the functions of s and t. So that is e to the x. Okay, that's st squared, e to the st squared, sine y. There's a sine, y is s squared t, and 2st plus e to the x st squared, and cosine y is s squared t, and here s squared. So that's the final answer for t derivative. Now for s derivative, rather than here t derivative, you are making s derivative, and similarly the product, and sum will be the final answer. Okay, you can do it yourself. Functions of two variable and chain rule can be expanded for general case. Suppose that u is a differential function of n variables, x1 to xn. Now, each of which has m variables. So each one is a function of t1 to tm. And we assume they are differentiable. Then, now, for example, in ti direction, we can get the partial derivative. Of course, here, the function u can be considered as a function of t1 to tm, so that if we try to make a partial derivative in ti direction, then first, every ti is involved, so that u x1 derivative and x1 ti derivative, u x2 derivative, x2 ti derivative, and so on. So that is on product rule. Okay, this is a product rule, and so that we can get such formula. Okay, write the chain rule for w as f of x, y, z, and t. X is function of uv, and y, z, t all are function of uv. And the w is function of x, y, z, t, and assume they are all differentiable. Then we can get w u derivative and w v derivative. Okay, this time let's try to do this one. Okay, round w and round u partial derivative. Then x, y, z, t, each of these variable, primary variable, involves u, so that first we make for the first primary variable derivative, and now x u. Of course, u is one of the secondary variable, and plus f sub y, y derivative and y u derivative, plus f z derivative and z u derivative, and f t derivative and t u derivative. And of course here round w over round v, and rather than u we are using v, then that's the final answer. These are primary variables for f, and these are secondary variables. Right? Z of st is given in this way, and f is differentiable. Of course, these are differentiable, and in this case, f is a function of x and y, but x is s squared minus t squared. Okay, you may think this is x, and that is now y. Y is t squared minus s squared. Show that the function, so once f is defined along with the primary variables x and y, and x, y are functions of two secondary variables s and t, then this whole thing can be considered as a function of s and t. And we want to check if G satisfies that equation. So we'll try to get the derivatives. Here we have to get S derivative and T derivative of Z. Okay, we write down here the formula. Okay, now G sub S, G S derivative, that is F, okay, F sub X and X S derivative, and F sub Y and Y S derivative. So F sub X, we don't know. So we are using symbolically F sub X. X S derivative is now 2S, right? And plus F sub Y, we don't know. It's not given explicitly. And Y S derivative, that is minus 2S. Okay. So that is the same as here 2S and then F sub X minus F sub Y. It's simplified. How about T derivative? Okay, F sub X, we don't know, so that we write down F sub X, X T derivative minus 2T plus F sub Y, again, we don't know yet. It's not given explicitly. And Y sub T, T derivative, that is 2T. So that is same as 2T and minus F sub X plus F sub Y. Okay. Now, let's consider this one. T times. So here, from these two equations, T times G sub S plus S times G sub T. Okay, T times G sub S, that is now 2S and F sub X minus F sub Y, and plus S times G sub T, that is 2T and minus F sub X plus F sub Y. Okay, for this one, 2ST, 2ST. So yeah, 2ST, and this one is F sub X minus F sub Y, and from here, minus F sub X plus F sub Y. Cancel, cancel, so it must be 0, so it is 0, right? Okay. Z is x cubed plus x squared y. Of course, this is a function of a differential function of x and y. Now, x is function of STU and STU. So we can consider z as a function of STU. So we may get that. And when also we can evaluate, we can get numeric value when STU are given in this way. So let's begin with this one. G sub S. Okay, what is G sub S? Oops. Okay, it's S derivative. Okay, but originally, Z is a function of xy, two primary variables. So we may consider and first x derivative for that one, z sub x. Okay, let's write down in this way. Z sub x and x sub s plus z sub y and now y sub s, right? Okay, in this way you can get it. Now, what is g sub x? 3x squared. X derivative is 2x and y. And, okay, that is x sub s. S derivative is 1. Plus z sub y. That's 0. And that is x squared. And y derivative is x squared here. and then y sub s, that is st. Okay, again, if you are asked to find the g sub s itself, then x and y must be replaced with these definitions. But we want to get the numeric value when STU are given in this range. So in this case, we can get x value from here. X is, now S is 2, T equals 0, U is 1, then it's 2, 0, minus 1, 2 plus 0 minus 1, which is 1. And how about y? Y is just the multiplication, 2 times 0 times 1, which is 0. So when STU are given in this range, then xy have these values. So from here, now there's a 3, and y is 0 plus 0, and times 1 plus x is 1, right? This is 1 times s and t. S and t, if you multiply, then 1 and 0, so that we have a 3, the final answer. Okay, let's try one more. We skip this one and try to get this one. Z sub u, that is. Okay, z is a function of x and y. X and y are primary variables, and xy are function of STU, so that as in the product rule, again, we do z sub x and x sub u, u derivative, plus z sub y and y u derivative, right? Okay, but we already know here z sub x and z sub y, and that is here 3x squared plus 2xy. You already know that one. Xu derivative, okay, that is minus 1, plus z sub y, that is x squared, we know that, and y sub u, that is st. Just a moment. It's s derivative, so that this portion must be tu, right? I'm sorry. It's s derivative, then there must be tu, and again t and u 0 and 1, so that 0, 1, so we have the same conclusion. That was a mistake. Okay, here y sub u, then now that is st. Okay, here, and we know that value is 3 from here, again, 3 times minus 1, and this one is again 0, that is 0, so that 1 times 0 is 0, so that the final answer is minus 3. For this one, you can get it yourself quite easily, following this technique. Okay. Implicit differentiation. We start with the function capital F as a function of x and y. Now y is a function of x. Then we can make here x derivative. Y is a function of x. Then we can make x derivative. First of all, here x itself involves x, so that here we make x derivative for capital F, and dx over dx. Of course, that is 1, and this quantity is 1. Now, f sub y and dy of dx, that is exactly the chain rule we learned, equals 0. Now, what we want to get is this one. So we move this one to the other side and divide by f sub y to get that formula. Okay. We want to find y prime if this implicitly, a function is implicitly defined in this way. Then if we want to use this formula, then we may have to define capital F by moving this one to the other side. Okay, so we recheck this one. Now y prime is f sub x over f sub y. So simply we try to get partial derivative of the function capital F, f sub x. Now 3x squared, that will be 0, and minus 6y, and capital F y, y derivative. Okay, that is a 3y squared and y derivative minus 6x. So from here we can get y prime equal minus, okay, the bottom y derivative 3y squared minus 6x divided by 3, that is y squared minus 2x, and top x squared minus 2y. That's the final answer. Okay. For this one, you solved this kind of problem in Calculus 1 by using the implicit differentiation. That is, now for this equation, x is the independent variable and y is a function of x. Then by using the chain rule, you can get this derivative. From this one, x derivative is 3x squared. Now, by using chain rule, first you make a y derivative, that's y 3y squared, and y x derivative equals. Now, x is involved here, x is involved here. So by using the product rule, you can reach it here. For this one, derivative is 6y. Now, derivative of x for that term is 6xy prime. Now, you can solve this equation for y prime. Then you can reach at this one. So you can get the same result. You can solve the problem either this way or in this way. In this case, the capital F is a function of xy. xy are independent variable for capital F. But y is a function of x. But when you consider capital F as a function of xy, then you may have this implicit differentiation. Now, y is a function of x. We reach that is y prime, and that is 1. So we can get this formula. Okay. That formula can be expanded for more than 2 variables. Z is a function of xy. Then we consider capital F as a function of xyz. Once it is implicitly defined, then now we have this form like this one. Z is a function of xy. Now it is defined in this way implicitly. Then if we call this portion as the capital F, then capital F is a function of xyz. They are independent variable for capital F. Now when you apply the derivative, for example, x derivative, then for the first component, it includes x, and for the second one, there's no involvement of x, but for third one, you have x involved. So, but anyway, by using the product rule, the chain rule, we have this one, f sub x, x over x, f sub y, y over x, f sub c, z over x. Now this will be 0 because x, y are independent variables, and that will be 1. So this portion is 1. Now that portion will be 0. And similarly, for that one, now that will be 0 because they are independent variables. And that will be 1. And this is y derivative. And we can solve this question for round c over round x. That is exactly this one. Now we can solve this one for round z over round y. That is this one. Okay? So we have this formula. Find round z over round x and round z over round y if x, y, z, an implicit function is defined in this way. Here we assume that z is a function of x, y, so that we can get that derivatives, partial derivatives. We'll try to find only one here. Round z over round y. Then from the formula, it is same as f sub y over f sub c. You may define capital F by moving this one to left-hand side and equal 0, but 1, after differentiation, 1 will disappear, so that you don't have to do that. Now, that is capital F. And capital F of y derivative is here. That is 0. And there is a y, okay, there's a 3y squared, that y derivative, so that 3y squared. Now, you have to be careful for that one. If you consider capital F, then capital F itself is a function of x, y, z. X, y, z are all independent variables. So that now we are trying to get here y derivative, so that that must be 0. Okay? Now, y derivative, then this is 6x. Be careful. When you are dealing with capital F, then z is an independent variable of capital F. So that y derivative, okay, that must be 0. F sub c. Okay, z derivative, this will be 0. And 3z squared and plus 6xy. By plugging these two over there, you can finish the computation. Of course, for round z over round x, that is minus of f sub x over f sub z. Okay, because we have already f sub z, the remainder part is this one, f sub x. Okay, let's try to get f sub x, x derivative. Then there is a 3x squared, and x derivative is plus 6, okay, yc, right? This term over this one, and along with this negation, that's the final answer. Okay. Okay, that's the end of section. Thank you.